Hello math students, today's video is lesson 5.5, more Ferris wheels. In lesson 5.3, we calculated the height of a rider on a Ferris wheel at different times t, where t represented the elapsed time after the rider passed the position farthest to the right on the Ferris wheel. So I was looking to the Ferris wheel in this picture, it'd maybe be like right there. On the Ferris wheel that we were looking at in 5.3, we had a radius of 65 feet. The center of our Ferris wheel was 80 feet above the ground, and the Ferris wheel made one complete rotation counterclockwise every 40 seconds. Based on this data that we calculated, and anything else that we know about riding on a Ferris wheel, we can sketch a graph of the height of the rider on the Ferris wheel as a function of time elapsed since the rider passed that position farthest to the right on the Ferris wheel. So we're going to consider this position to be time t equals 0. If we go back and look at our 5.3 notes and plot all of the points that we calculated, it should look something like this. When I go and connect the dots, more or less, this is the shape we end up with. And hopefully when you're doing it, it looks a little bit better than mine. This type of graph should look familiar. This is something you may have seen in a science class when you're studying light or sound. Light and sound waves are this type of shape. This is called a sine wave. Or another fancy word is a sinusoidal function. That just means that it is a function that can be modeled using sine. As I was graphing this, it probably was a pain, or it was a pain, to have to go and plot every single point on here. On a circle, though, if this is my Ferris wheel, I know at the farthest right point right there, that is the height at my center. That's my 80 right over here. If I was to go all the way around the circle once, we would end up 40 seconds later at the exact same point we started out at. Halfway around the circle, if I come over here, this is 20 seconds later. I am still at the same height I started out at. If I go a fourth of the way around the circle to the very top, that's 10 seconds in. I am at my highest point, which is 145. And then 3/4 of the way around at 30 seconds, I am at my very lowest point, which is 15 feet. So if I know these 5 points, that's enough for me to be able to graph the heights after one full rotation around the circle. Once I know one full rotation, it's the exact same thing over and over again. When we did it in 5.3, we only went to 80 seconds, but every 10 seconds, I'm either going up to the highest point, down to the middle, or down to the bottom point. So 10 seconds after 80 seconds, I'm back at the very top. So at 90 seconds, I'm up at 145. 100 seconds, I am on the very left side. So that's what it would look like if I was to continue graphing this. If I want to write the equation, when we did it in 5.3, every single time we were calculating our heights, we were doing 80 plus 65 times the sine of some angle. The way that we found our angle was we found the angular speed, which was 360 degrees divided by 40, and then multiplied it by the time. So the angle was angular speed times the time. So I can put in my equation, angular speed is 360 over 40 times t. This 80 right here represented the radius of, sorry, the 65 was the radius. This 80 represented my center height. The 65 was the radius. And the 40, that right there, was the time for one rotation. But the entire 360 over 40 was that angular speed. Ferris wheels are not all the same size. So if I wanted to create a new Ferris wheel that maybe had a radius, I'm going to make it smaller. I'm going to say it's 20 feet. My center height, I am going to say is 30 feet. The time for one rotation, maybe is 20 seconds. And then I'm going to change this up and I'm going to go clockwise. If I wanted to create a graph for this, I said that my center height was 30 feet above the ground. So as I start off, I'm at 30. I also said that it takes me 20 seconds for one rotation. So after 20 seconds, I'm back in that same spot. Halfway around the circle, if I go halfway around from here to here, I am in the same spot. Halfway around the circle was 10 seconds. So 10 seconds, which I already put that on there. And then if I go a quarter of the way around the circle, I'm at my highest point. So at 5 seconds, I am going to be 20 feet up. So I go up 20 is 50, except for I'm going clockwise. So I'm actually going down to 10. I would come back up to 30. At 15, I would go up to 50. And then I just repeat this. So I'd go 5 seconds, 25. So every 5 seconds, I'm going to put a point on here. And then when I connect it, I want to make sure I do it smooth. Don't just go do straight lines, because a circle does not just do straight lines from the highest point to the lowest point. It's a smooth transition. And try to connect the dots as best as you can. It's a little harder for me to do it on here, but if I want to write an equation, do the same thing we did on number 2. My center height was 30. My radius was 20. I did one rotation every 20 seconds. So if I simplify this, this is 30 plus 20 times the sine of 18t. At the beginning, we were thinking about the graph of the height of a rider on a Ferris wheel with a radius of 65 feet, and my center was 80 feet off the ground. I made one revolution counterclockwise every 40 seconds. If I decided to make the radius of my wheel bigger. I want to see what that's going to do to the graph. This is the graph on number 1, so before I changed anything. Let's say I want to make my radius bigger. So if I change my radius to be 100, this is what my graph looks like. The center is still the same. All that I've done to my graph is I'm going to say that it's taller, or really it's stretched away from the center. If the radius became smaller, so if I decided I wanted my radius to be 20 instead, we can see the center is still the same. It takes the same amount of time to go through one full rotation, but the whole thing is shorter, so it's squished towards the center. If the height of the center, if I wanted to make that higher, so let's say instead of having the height at 80, I wanted to have the height be up at 20. Sorry, up at 100. Everything is the same except for I have just moved the whole graph up. And if I wanted to have the height of the center of the wheel lower, so if I change it down to 50, same thing, it just moves the whole graph down. Let's say I want to have the wheel rotate faster, and so instead of taking 40 seconds, I want to make it be 15 seconds. As you can see, it's been squished in, or I'm going to say that there is a shorter wavelength. And then if I make the wheel rotate slower, so I'm going to have it go 75 seconds for a full rotation, we can see that this is going to have a longer wavelength. We can also see what changing each of these things is going to do to my equation. I'm going to write my equation as y equals a times sine of bt plus d. If you remember, we said a was the radius, d was the center height. I've just moved it to the end. And this b right here is my angular speed. So that was just 360 over the time per rotation. So if my radius is larger, that just means that A is bigger. If my radius is smaller, that means A is smaller. If the height of the center of the wheel is higher, that just means D is going to be a bigger number. If the height of the center of the wheel was lower, it means D is smaller. If the wheel is rotating faster, that means that B is going to be bigger. But you remember we said that means my wavelengths are going to be shorter. So the bigger number means it's going to squish it in. And if the wheel is rotating slower, that means that B is going to be smaller. So we're going to go over 2 more examples and then write down a couple of last notes that are just combining everything all together. This example, once again, I want to write the equation of the height of a rider for each of these following Ferris wheels. This first one, I'm telling you that the radius is 30, the center is 45 feet above the ground, and the angular speed is 15 degrees per second counterclockwise. So when I'm writing my equation, I have y equals, so I've got my radius is 30 times the sine. That b is my angular velocity, so I'm going to put just 15 times t plus the center of the wheel is 45 feet above the ground. So that would be my equation. And b, it tells me the radius is 50 feet. The center of the wheel is at ground level. And that makes 1 revolution clockwise every 15 seconds. So for my equation, I have 50 feet radius. It makes 1 revolution clockwise every 15 seconds. So if I find my angular speed, I'm going to divide by 15. And then I'm at ground level, so I'm going to add 0. Because I'm going clockwise, I'm going to go ahead and put a negative in front of the 50. That just means that it's going to go down first instead of going up on my graph. If I want to simplify this, this is y equals negative 50 times the sine of 24t. So final notes for this equation right here, and for everything I'm doing right here, we're going to do it in the context of the Ferris wheel. Y represents the height on the Ferris wheel. T represents the time after passing point A. So we have a midline. The midline, if we were to look on our graph, so if I had something like, draw that a little better, pretend that's my equation. The midline is what's exactly in the center. So the midline lies halfway between the maximum and minimum points on the graph. This depends on the height of the center of the Ferris wheel, and it's represented by D in my equation. The amplitude is the distance from the midline to either the maximum or the minimum. So on my graph, if this purple line is the midline, then the amplitude is this distance from the midline to the top or the midline to the bottom. This depends upon the radius of the Ferris wheel, and it is represented by A in the equation. Finally, the last thing we have is the period. The period is the interval before the graph starts repeating itself. This depends on the time it takes to complete 1 rotation of the Ferris wheel. In my equation, B represents the angular speed of the wheel. So if I want to know the time it takes, my period is just going to be equal to 360 divided by B.